Exercise 81, let's talk about linearization. More precisely, it's linearization of a semi-linear map. So what should be the setting? Let's say I try to give a very general setting. Let's say if R is a commutative ring, with a let's say just an operator, sigma over 8, then we consider D. A free R module. And now, if we define a functor, operator defined over D, more precisely, semi-linear functor. What does this mean? It means that if you take element from this free R module, let's say Ri xi, indexing set, then semi-linear is just telling that the Frobenius acting, not yet the Frobenius, so this operator acting on this element. So if it's linear, then it would tell you that this equals Ri Frobenius xi, right? This is linear. But semi-linear is just saying that this. And the reason I mention operator is because this is a classical situation. So let me give you an example. So if, let's start with a very easy example. Let's say R is some finite field. So denotes phi the Frobenius defined over it. And then if you consider those FQ vector spaces, and then we call this Frobenius big phi to be that. If you take an element, so just look at elementary tensor or just generating element. So if you take any Q X in D, then this is defined to be just semi-linear sigma of X and the Frobenius X. The reason is that whenever we define Frobenius, it should be compatible with the known structure usually. Here, you could has FQ vector space, so over FQ there is already Frobenius. But when you fix spaces, you could define how is this operator Frobenius acting on that basis as you want. But we require this Frobenius defined to be semi-linear in the sense that when acting on the coefficient which is in FQ, it is given by not linearly, which means trivially on this coefficient, but instead it's acting through the known Frobenius. This is called semi-linear. Actually, this is example, so not necessarily in this case. You could take small k, just some perfect field, characteristic, that's a characteristic P, and then you take this width ring. There, there is again a canonical Frobenius defined there. Basically, it sends elements in this width ring to reason to its pth power. So here, reason this formula, you don't require the small k to be perfect. Just characteristic P should tell you that Frobenius is defined this. So anyway, I'm saying that there is again canonical Frobenius, and then if you define free WK modules, then you could define, okay, I'm going to define a semi-linear Frobenius here. When you look at the coefficients, let me maybe denote Frobenius WK to refer to this. And so when you're acting on lambda in WK and then some element x in D, then this is defined to be Frobenius WK acting on lambda and then Frobenius x. You fix the basis of it, and then you could define using matrix. But you cannot use the matrix multiplication to really describe this operator operator phi, because this is not linear transformation. It's not linear, it's semi-linear. Okay, after this example, let's come to our exercise today. So the exercises show that to give a semi-linear map. So phi is some not necessary for Frobenius, it's some semi-linear map, and D is some free vector, a free module, okay, is equivalent to give a linear map. This linear map is defined as follows, which is called the linearization of phi. So usually there are many ways to write this. Sometimes people write phi star, sometimes people just write 1 tensor phi, and this is just different notations. Okay, so let's define this map. It is denoted in this way from d phi to D, but more precisely, this defined to be, suppose we are over R, so that this is R, tensor with D, not as R module coming from the R module structure of D. I mean, R regarded not, how is R regarded as R module? Not trivially, but through the operator. What does it mean? So let's first describe. Let me first describe what is this structure here. So this means that, so the elements here is still equal, elementary tensor equals 0, right? R tensor X. But this R operation, or this R module structure. So how do you regard, how is the R module structure here? So let's say take whatever lambda in R, I'm going to describe what it is. So this is defined to be our module structure is defined to be, usually you should be able to define it either on the first component or on the second component. It's still true, but let's say firstly, if you're acting it on the first component and then tensor x, here it's not trivially just use the multiplication inside R, because this is a ring, so you could say, okay, this is the element of R, this small is the element of R, I'm just multiply it together. No, I'm looking this R as R module itself, but through the map phi, which means we really want to take element lambda acting on element of R on the left component part. I'm going to define it as Frobenius, no, not necessarily Frobenius, this map phi acting on lambda, and then use the multiplication inside R, inside the ring R. Or you could acting on it on the second component, then as usual, just because x taken from this R module D, then just use the R module structure there. And this is implies something. This implies that how do you move R from right component of the tensor to the left, and conversely, this is telling you that, so just take this example again, R tensor with, even let me just use slide notation to make this not so confusing. So let's say S, let's say R1, R2, lambda mu, let's say lambda mu x equals, so this lambda is in R, mu is in R, x is in D, this equals, we want to move some element in R from the right hand side to the left hand side. What you do is Frobenius of mu or phi of mu, and then multiply on the element on that part. Okay, this is also tell you that if you really want to move something from the left hand part to the right hand part, you not just move it. In some sense, you're applying the phi inverse on that element, right? But that's not always doable. If you could, which means you start with some element, the image of Frobenius, and then you could also move it to the right hand side. Right. Wait a minute, it is well defined. Basically, my sub-question is, suppose you have two mu1 and mu2. Find mu1. Question: can I do that? Find mu1 lambda. Let's say find mu1 tensor x. Let's say if find mu1 equals find mu2, then basically you're telling me that this should equal to this, but can I, if I claim this is the case, by the claim this is then mu1 x, this is mu2 x, are they indeed the same? Are they necessarily the same? I'm not sure. I don't think this is, but in some example this is true. for the examples when K is FQ, we know that Frobenius is actually always bijective. Because this is perfect. Okay, and so there's no such a problem. In that case, in particular, it is injective. But in general, I think this is just telling us that you're not really allowed to move from left-hand side to right-hand side unless you know Frobenius is injective. Let me think it for a while. This implies that mu1 minus mu2 is in the kernel of phi, right? And then one tensor mu1 of x equals one tensor mu2 plus phi of plus something in the kernel of phi. Let's say C, and then tensor x. So this is just one tensor mu2x plus one tensor C of x. But C is in the kernel of Frobenius, but it's still inside R. And so, which means you can still move it to the left-hand side, but by our rule, this will be Frobenius of say acting on 1 and then tensor x. But this is the kernel, so this is 0, and so this is 0. And so indeed, these two are the same. So actually, this is well defined. Okay, so this could be taken as our first exercise today. How to describe the R module structure over this R module, which is denoted by d of phi in the literature. So okay, so let's come back to our exercise question. So the question is to ask you to show that to give a semi-linear map is equivalent to give a linear map from the which linear map? I haven't defined. Its notation is called one tensor Frobenius, and it's defined not over D but d phi. What is d phi is just described. So now let's describe this linear map. This linear map is just for elementary tensor. Let's say R tensor x. This is mapped because it's a linear map. This is just R linear, and then just 5x. This is how it is defined. So this is the exercise I ask you to show that to give this is equivalent to give, which means if you're given a semi-linear map, then you could construct a linear map by linearization, which is okay. I already constructed it, right? I have constructed it, and then you have to show that given a linearization, you could go back to the semi-linear map. That's the question. Okay, so before we prove that, let's give one more remark. So this linearization, as its name indicates, is our linear map. Okay, secondly, let's check how to say, let's really check. So actually we don't have to check, we already checked everything we want, but just to convince you, let's check something like this is really our linear map, even compatible with the R model structure we just described over the define. So let's say if you have R1 acting over this tensor, and you want to map through this linearization, and then as we expected, because this is linear map, that this should be mapped to if we just use this definition here, then you could write it more explicitly. Either you use this, and then this is mapped to R2 phi of R1x, or you use the R model structure on the first component as we described. This would tell you to be phi R1, R2 tensor x, then this map to phi R1, R2, and then phi of x. And so they're the same, because as we require this RB commutative ring. Okay. Okay, so that's it. So now we're only left to prove the exercise. Basically, we just want to show how to recover Frobenius from its linearization, right? Or big phi or one tensor phi. So the way we recover is as follows. So we want to construct them. So we already have this linearization. To D, and now we want to construct map from D to D, right? So what we do is we define by composition. So here, let's say over R, it's just isomorphic to D itself. So element here is mapped to one tensor x, right? Okay, so we're going to put Frobenius tensor identity here. So let's just describe it on an elementary tensor. That's enough. So R tensor x is mapped to Frobenius of R tensor x, and then through our map here, linearization, this gives you phi of R and then phi of x, and you say this is altogether, this is the semi-linear map for Frobenius at the beginning, right? And so we have recovered linearization from recover the semi-linear map from the linearization. Okay, so let's even check this is actually that's already good. Okay, let's just do some small computations to have you better understand this. So let's look at our construction. So we start with R tensor X. Let's say if you mu, then this is mapped to phi of mu, phi of R, and then X. Through the linearization, this is mapped to phi of mu, phi of R, phi of X. And we know that R tensor over R with D, this is the same as R mu X. This is mapped to phi of R and then mu X. And through the linearization, this is mapped to phi of R, phi of mu X, which is phi of R, phi of mu, phi of X. And this is the same because we require this R to be a commutative ring.